in the name of God. We would like to present this paper for publication in STMIO International Conference. This research have been founded by Ferdowsi University of Mashhad, FUM, Iran. The work has been carried out by myself, Daniel Gandumzadeh, as part of my PhD thesis under the supervision of Professor Abbaspour Fard. This presentation consists of several parts such as introduction, novelty, material and methods, results and discussion. Ultrasonic waves can be generated based on various principles such as piezoelectric and magnetostriction. Piezoelectric materials are used in high-frequency applications, but fabricating process of such materials are complicated and difficult. Also, these materials for producing ultrasonic waves some problems such as fracturing and cracking of crystal arrays and also lower power density and overheating occur. These advantages limit the use of piezoelectric transducer for high power application. As an alternative, magnetostrictive transducer are used to produce ultrasonic waves with frequencies ranged between 2 Hz to 2 MHz. Magnetostrictive transducer have many advantages such as simplicity, reliability, durability, and low cost, and they can generate more powerful sound. The core is made of magnetostrictive materials which are found in nature positively and negatively. In other words, when exposed to magnetic field, some are shortened, for example nickel rods, and the negatively magnetostrictive materials such as nickel can be used without the use of a permanent magnet. Giant magnetostrictive materials include manganese cobalt silicon alloy, cobalt ferrite alloy, cobalt vanadium alloy, terbium dysprosium ferrite alloy, or terphenol D ferrite gallium alloy or galphenol. These alloys are high performance materials for the purpose of magnetostrictive transducer, but they have some disadvantages such as poor ductility, lack of machining ability, having rare and radionuclide elements, and requiring high temperature and pressure in the production process. Moreover, some of these materials are very expensive. Some natural elements such as nickel inherently have to somehow magnetostrictive properties. Nickel is advantaged because of having high tensile strength and low electrical impedance, so that this material can be used in low frequency and high power applications. Furthermore, natural sources of nickel are found abundantly and available at an affordable price in the market. Novelty. Various influencing parameters on the behavior and performance of magnetostrictive transducer have been investigated in software environments, but very limited research works have been published in conjunction with the effect of core geometry on their performance. Evaluating the performance of simulated cores in the software environment is very important, because according to the type and purpose of the research and application, different geometries of core can be used. In this study, it is tried to investigate some feasible ways of using low-cost and abundant materials such as nickel in magnetostrictive transducer, which is a challenging issue because of their weak magnetostrictive effect. Therefore, various cores with different geometries but the same volume and lengths were considered to analyze their behavior as a key element in the performance of magnetostrictive ultrasonic transducer. The simulated runs were performed using JMAG Designer software environment. In this research, the effect of coil parameters on the performance of a magnetostrictive transducer are studied in depth. These are frequency and core lamination factor in X or Y and Z axis. The hypothetical magnetostrictive transducer assumed to have a tapered nickel core. Having reviewed the literature, limited research works have been conducted on a tapered core of magnetostrictive transducer. In addition, the present research performs a closer look at the behavior of conical core of magnetostrictive transducer via numerical simulation and analysis using the JMAG Designer. This software is able to directly calculate the amount of magnetostrictive force along with other magnetic parameters. The aim is optimize the transducer by maximizing the longitudinal magnetostrictive force or MAGF fluctuations, which is the key factor in the transducer performance. Then the design and manufacturing process of this transducer were explained. In addition, the performance of the magnetostrictive ultrasonic transducer in creating the cavitation phenomenon to disperse waterproof paint in aqueous solvent was investigated by image processing. Materials and method. In this investigation, the core geometry is the main independent variable. Hence, 9 different core geometries with the same volume and lengths were considered. The geometric shapes of these cores are as followed, or this table: cubic square cross section and rectangular with aspect ratio of 1.9, cylindrical, circular section and ellipse of 1.9 aspect ratio, and tapered core with cone angle of 7.5, 15, 30, 45 and 60 degrees. The propagation of ultrasonic waves in longitudinal and radial direction as their corresponding magnetostrictive force were considered as dependent variable. The main objective of this study is to evaluate the effect of core geometry on the magnitude and variation of magnetostrictive force, mainly in longitudinal direction. The core specification of the simulated magnetostrictive ultrasonic transducer assumed to be constant during simulations. After casting the pure nickel in the induction furnace, the machining process of the core, housing and cap was performed to achieve their desired dimensions. In order to evaluate the performance of the nickel magnetostrictive ultrasonic transducer, a waterproof paint dispersion test was used. In this test, the dispersion rate of waterproof paint in the water was evaluated. Results and discussion. Figure 1 shows the maximum magnetostrictive force in the longitudinal direction. According to this figure, the highest longitudinal maximum magnetostrictive force is observed in the cylindrical core with ellipsoid section of aspect ratio 1.9, and next in the core rectangular section with the same aspect ratio. In the tapered core, as seen, by increasing the cone angle, the maximum longitudinal magnetostrictive force is almost decreased in a piecewise linear manner. It can be concluded that the elliptic cylinder core aspect ratio 1.9 provide the highest magnetostrictive force along the z-axis or longitudinal direction. When cores with different geometries and different demagnetizing factor are exposed to the same external magnetic field, they would exhibit different value of I and B. So their magnetostrictive strain would also be different, because magnetostrictive strain depend on intensity of magnetization. Furthermore, by increasing the ratio of length to diameter of core, the amount of apparent permeability and the magnetizing factor increase linearly, since the length of the core in the current study is constant and equal to 100 mm. By decreasing the average diameter of core, the demagnetizing factor would increase. By increasing the cone angle, the longitudinal magnetostrictive force is decreased because the uniformity of magnetic flux density is decreased. In order to evaluate the uniformity or ununiformity of flux magnetic lines around the core of magnetostrictive ultrasonic transducer, these lines achieved in JMAC Designer software for all 9 core geometries. The number of magnetic flux lines which placed on XZ plane were counted. According to this figure, increasing the maximum radial or longitudinal magnetostrictive force in 30 degrees cone angle is due to increase the different value between the number of the left and the right magnetic flux lines. In ultrasonic transducer, the variation of generated force in longitudinal is the key factor affecting the medium being processed. Therefore, the study of force variations in longitudinal direction is of great importance. Increasing the range of magnetostrictive force variations along the z-axis increases the range of pressure variation acting on the medium. By increasing the range of pressure variations, the medium, the cavitation phenomenon takes place with higher severity. Comparison of the range of magnetostrictive force variation along z-axis for the different cores is presented in this figure. According to this figure, the highest longitudinal force variation is observed for the elliptic cylinder core of aspect ratio 1.9. Moreover, among the tapered cores, although they cannot be seen a clear trend in the evaluation of longitudinal force amplitude. The highest for amplitude is seen for the tapered cone with cone angle of 30 degrees, because it seems that the changing the cone angle, the natural frequency and also possible change in vibration lead to increase the amplitude of the longitudinal force for the tapered cone with cone angle of 30 degrees. Figure 5 shows the variations of MAGF components versus frequency in the tapered core cone angle of 30 degrees. As seen by altering frequency, the maximum axial MAGF, mainly left figure, are irregularly varied. However, a generally declining trend can be drawn for them, because this is mainly due to the fact that by increasing frequency, the eddy current and hence the magnetic flux loss are increased. On the other hand, at low frequencies, the magnetostrictive hysteresis is independent of frequency. Accordingly, it has been reported that reducing the frequency increases the displacement of magnetostrictive actuator. According to right figure, the fluctuation of MAGF along the z-axis decreases with increasing frequency, because reducing the frequency increases the eddy current penetration depths in the conductive material. In other words, it provides a deeper eddy current scheme. Moreover, by increasing magnetostrictive materials, high power audio sources can be generated at lower frequency. Figure 6 shows the MAGF components versus lamination factor along the X and Z axis in tapered cone with cone angle of 30 degrees. By increasing the lamination factor along X axis, the longitudinal MAGF is fairly affected, mainly left figure. At lower lamination factor, no tangible change in force is seen with altering the lamination factor, while with a very high lamination factor, the force decreases remarkably. By increasing the lamination factor along z-axis, the maximum MAGF increases. According to right figure, by increasing the lamination factor in X direction, the fluctuation of MAGF along the z-axis remains almost unchanged. However, an exception is observed at lamination factor of 70%, which is, according to figure 7, can be related to the higher magnetization of core at this lamination factor. By increasing the lamination factor in Z direction, the fluctuation of the MAGF along the Z-axis is increased, which is an important measure in magnetostrictive ultrasonic transducer. Because according to left figure, by increasing the lamination factor, the relative permeability increases. This is mainly due to the increase of relatively permeability, mainly left figure. In other words, the ultrasonic performance of these magnetostrictive transducers improves by increasing the lamination factor along the x-axis, so that the fluctuation of the MAGF along longitudinal direction increases. According to this figure, since the dispersion of waterproof paint at the bottom of the glass bottle is non-uniform, it is observed that the cropped image at the lower end of the left side has an occupancy level of 62 at 10 seconds, and at the end of 60 seconds the occupied area reaches 81%. But at the lower right side the occupied area is initially 28% and at the end about 100%. But in the middle parts the paint dispersion speed increased from 20 to 40 seconds, so that in 40 seconds more than 80% of this area are occupied by blue paint. At the upper parts up to 40 seconds the dispersion speed is very low, but it is observed that between 40 to 60 seconds this increases rapidly, so that more than 90% of this area are occupied by blue paint, because by increasing the Reynolds number, which indicates turbulence in the fluid, tails are created on the new bubbles, which intensifies the cavitation phenomenon and increase the tendency to last longer after the dispersion of the main bubbles. Conclusion: the elliptic core had the highest maximum axial magnetostrictive force. However, optimal ultrasonic transducer should have a maximum range of pressure variation in the medium. Therefore, the range of the magnetostrictive force variations along the z-axis should be maximized. The biggest range of magnetostrictive force variation in the longitudinal direction was observed for the tapered core of having 30 degrees cone angle. Since the fluctuation of MAGF in the longitudinal direction of core is an important parameter for generating the ultrasonic waves, the results show that this fluctuation decreases with increase of frequency. Moreover, by increasing the lamination factor in the x-axis, the fluctuation of MAGF along the z-axis remains constant. However, the ultrasonic performance of this magnetostrictive transducer improves by increasing the lamination factor along the x-axis. The results show that the transducer is able to disperse more than 90% of waterproof paint in the glass bottle after 60 seconds. It was also observed that the cavitation phenomenon initially moves the bubble paint at the bottom of the glass bottle and then cause to disperse the paint toward the middle layer and finally in the upper layer. Based on the result, this transducer can be considered to remove pesticide and other impurity from the surface of agricultural products. And our teams, some references, and thanks for your attention.